of nanotechnology in the whole world market. But I have to tell you that these numbers cannot really be trusted, because the one company is producing a nanoparticle, the other company is using it for the one product, a second company is using this product to build up another product, and so on. And so this one nanoparticle is counted 3 or 4 times maybe, and these are only estimates made from different institutions. But what really can be seen, a shift to really high numbers, and for 2020, this Rocco and Bainbridge company is telling us that we will end up at about $3 trillion of dollars worthy the market of nanotechnology. So this is a huge, really huge number. Okay, this I'm not going to read in front of you now. Depicted from the 2009 nanotechnology Nano.de report. So this timeline here is for 2008, and then 3 years later we end up at 2011. So at the moment we are here in this field, and some of the named inventions or applications are already actually. So this is a bit mixed up, but for the year 2008, this was the best known idea about the market. What will be the applications in industry? Some sectors: civil security, construction engineering, environment and energy, and so on and so on. You can read it, and many of these applications will come later on. The same for textile, automotive engineering, chemistry, and optics, electronics, medicine. So you see many, many applications of nanotechnology already at the market, even if it's a rather new technology. Good. Now we become a bit more scientific or basic. Size matters. I've already told you this in the first introduction. When we change the size of a material, we make it smaller, we enter the nano world, then fundamental properties start to change. There could be surface effects which are changing because we have a really high quantity of the atoms at the surface then, and not inside of the material, not in the volume. What plays a role are quant effects, optical and electrical effects, for example, the tunnel effect or the wave-particle dualism. And what plays a role are cooperative effects, for example, magnetic properties, the paramagnetism, as I already shown you with this evolutionary nanotechnology, the core shell nanoparticles, for example. When we talk about nanocomposites and the size of the constituent particles, we see that the surface area fraction is really, really, really increasing when we lower the diameter of the particle. So with particles in the size of only 1 or 2 nanometers, then already 10% of all the atoms are at the outside, are at the surface. And you can imagine that it makes a difference in the behavior of the material if only 0.001% of the atoms are at the surface, or if 10% are at the surface. So all of these atoms at the surface can be used for reactions, for example. And this interface then acts, of course, as a third phase. An example here for quartz. All of them 50 kilograms. 1 cube of quartz, 50 kilograms, is 27 centimeters in each direction, and has then a surface area of about 0.5 square meter. When we lower the size to 1 millimeter cubes, we have already 120 square meters of surface. And when we lower it to 1 nanometer, we already have 12 square kilometers surface. So this is the trick behind it here. Many of the atoms are then at the surface. Are you familiar with the term percolation threshold, or should I explain it? Not familiar? We have one material, a filler material, incorporated into a matrix, and the filler material can build out a network then, so that when we start here, we have, for example, as matrix a polymer, and the filler inside this matrix are the multi-volt carbon nanotubes, and we want to know how many or how big the portion should be that a whole network is building out. So when an electron starts to flow here, can it go through to the upper side, or is there no real network built out? And this is not only dependable on the amount of the filler, but as well on the aspect ratio of this filler. This is why nanotubes are the right choice for materials which have this conductivity. You have to think about it that polymers, most of the polymers are non-conductive, and if we want to make them conductive, we can incorporate different kinds of fillers. And when we talk about carbon fillers, we could use spheres here, which have the aspect ratio, so the length to the diameter is 1. Then we would need about nearly 30% of filler that a real network builds out. And you can imagine that then the properties of the polymer will change dramatically. Not only the conductivity, but all the other properties will be affected. But if we use carbon black, it's already better. If we use carbon fibers, we only need about 6 to 7%. And if we use carbon nanotubes, Fibril is just a specific type from Hyperion Catalysis, an US company, and we only need about 1.5% of such a filler, and we really have a conductive material then. And by using 1.5 of such nanotubes, I can tell you, or I have slides later on, that the mechanical properties are changing, are getting better as well. Good. When we think about nanocomposites, if we want to make better material by incorporating nanoparticles into another material, into the matrix, we should be aware that this has to be done with good dispersion and good distribution. So this is here the point D. Here we have agglomerates, so they are not well dispersed. And here, of course, they are good dispersed, but the distribution is bad, and so on. So this is what we are searching for, or what is the best to achieve the highest properties. Size matters not only, for example, here with this percolation threshold for conductivity, but as well could have an effect on optical effects. Here, absorption and scattering of titanium dioxide. On the one hand, we use titanium dioxide in wall paints, that they have a bright white, brilliant white. But here we use titanium dioxide particles in the range which is marked yellow here, 300 to 500 nanometers. Then we have a high scattering, and when the sunlight hits the surface, because of this high scattering, we have a brilliant white. But if we want to use them in sunscreens, we need a high amount of absorption. So this is the curve here for absorption. And particles in the range of 30 up to 100 nanometers are used then in sunscreens because of this high absorption, so that the UV light doesn't harm your body and is filtered out by these titanium dioxide particles. So one and the same material could be used in different applications. Both are nanoparticles, but on the with the slower ones we have the high absorption, and with the bigger ones we have the high scattering. Mechanical properties, of course, change when we talk about nanostructured materials. Well, you can read them: strength, hardness, wear resistance, and so on. When we talk about metals, all of these properties are dominated by the grain size. And in general, when we lower the grain size, we achieve higher properties: higher strength, higher hardness, better wear resistance, and so on. Well, okay. The grain boundaries are very important, and you can imagine when we make the grains smaller, many atoms again are at the boundaries, and therefore they are acting a bit different than with bigger grains. Well, we can produce metal samples with different grain sizes by different techniques: nanoparticle deposition, electrode deposition, or low temperature milling, for example. And here is an example then, so-called, or let's call it, normal piece of metal. It's a tin, and in this case, totally conventional material. We see the size of the grains here, about 10 to 20 microns. If we are nanostructuring this material, so this is the same magnification. This is 10 microns, and this is 10 microns, nearly the same material, but it's a nanostructured nickel paste coating here. We cannot see the single boundaries here, or the single grains. So we have to look into detail into it. With a 15,000 times higher magnification, we see the single grains then. Well, and this helps us to create higher performance materials then again. So in the coarse-grained metal, only one atom in 100,000 is at the grain boundary, really at the surface here. And in the nano-grained equivalent, about a quarter of all the atoms is at the grain boundary. And an example here for such a thing with aluminum alloys, the yield strength of aluminum alloys, the lower curve, stress-strain curve. I think everyone is familiar with such curves. With the coarse-grained normal aluminum alloy, we have about 250 megapascal maximum stress, and by lowering the grains to lower sizes, about 30 nanometers, we can shift the stress up to higher levels, and even about 750 megapascal for aluminum. But when we look at the strain, of course, this is accompanied by an embrittlement. So this increase for aluminum alloy here is about 4 times, and with copper, I could show you the same with a tenfold increase. This can be done for polymers as well. We want to have, or when we look at the stress-strain curve of a polymer, many of them look like this. Relatively small stresses or low stresses, but higher strains. When we fill them with particles or with fibers and so on, with classical fillers for polymers, we end up with the red curve. We have a higher Young's modulus, we have higher stresses, but an embrittlement as well, lower strains. And when we use nanofillers instead of classical fillers, we have nearly the same shift up to these higher stresses, comparable with the classic filler, but nearly no embrittlement. So this is here the trick behind the nanofillers in polymers. Well, I think I can skip this, only 2 words or 3. What's shown here in this curve is with lowering the particle diameter of gold, for example. Gold is in bulk, when it's greater dimensions. It's a totally inert material. When we lower the diameter of such particles to about 4 nanometers, it becomes very reactive. And again, it's because many of the atoms are then on the surface and not inside of the volume. So a totally inert material can become a powerful catalyst if we make the diameter of the particles less than 5 nanometers. And this carbon monoxide oxidation activity is just the measuring method behind it. Nanoparticles can interact with living cells. This is used on the one hand, for example, in wound dressings or things like that, or if we have bactericidal applications with silver compounds. So the slow release of silver ions out of the silver particles. But on the other hand, if this is not really controlled, or we do not know it so far, if, for example, in the deodorants, the silver particles which are incorporated, if they can harm our living cells, not only bacteria and viruses and so on. And so this is a bit controversial at the moment. But if we gain real control over the size, and if we gain the knowledge at which size they're only attacking bacteria, for example, or viruses, then this can be of real big use, because with silver nanoparticles, then maybe this could also work for the HIV virus, and I think this would be a great benefit then. So this silver particles, or the ions out of the silver particles, are really toxic for bacteria and so on, and so we can use them in medicine applications, for example. Again, one slide to magnetic behavior of nanoparticles. Again, particles, when we lower the size, we are still talking about that size matters. For example, I think it's iron here. I'm not going to tell you what is magnetism about, because I've learned this many years ago, and I'm not really familiar up to now. But what is the thing behind it? We have magnetostatic interaction and we have exchange interactions. And what is happening is that domains are built out, and if we have a bigger piece of iron, there are these domains, and therefore all these domains, when we make a sum out of them, we end up with no magnetization. So this pure bulk iron, this soft iron, is not magnetized at all, because this and this is 0, this and this is 0, and so on. But if we lower the size, really lower it, there is a critical size at about 100 nanometers. A single domain is then favored, and then this particle can be magnetized. And this is used, for example, for hard disks and so on. Good. So now we know a bit that the particle size really matters. Now I want to tell you that nanoparticles are surrounding us everywhere. We are not only producing them because we want it. It's happening by instance, of course. So there are many naturally occurring nanoparticles in the Earth's crust, in the oceans, in the atmosphere, and even in deep space. What is a bit changing nowadays, the amount of manufactured nanoparticles is increasing. And so maybe in many years, the amount of manufactured nanoparticles will be higher than the amount of naturally occurring, but this will be far away in the future. Of course, there are then controversial discussions, Feinstaubbelastung and so on. I think everyone is familiar with this. So this is not only because of our diesel engines and so on. It's even because forests are burning and so on. But of course, many of the man-made particles are a bit different to the naturally occurring ones, and maybe our body needs some years that he develops methods to get rid of them again and so on. So controversial discussions, of course, and I will not say that we are not verantwortlich, responsible for lung diseases and so on, but it's not only the industrial production of nanoparticles and diesel engines and so on. It's of course a big amount is of course that there are naturally occurring nanoparticles surrounding us. The effects of this naturally occurring and even the man-made is very, very multidisciplinary subject, and there has to be made lots of research that we will know it in some years what really is happening here. Some examples of naturally occurring nanoparticles. First are aerosols. For example, a volcano. You can imagine that in this that these are not only bigger particles, but lots of nanoparticles in there. As I already told you, forest fires and so on. Here, an example for hydrosols, hydrothermal vents down in the ocean. They are producing nanoparticles as well, or this should be supernova explosion, or even some bacteria can produce nanoparticles. Here inside, I think you see it a bit difficult here. There are black particles. These are magnetic nanoparticles produced by this bacteria. When we look at the atmosphere, atmospheric nanoparticles, so the particles are distributed in a gas, and they are lowering then from the higher from the space or from 10 kilometers up in the air. And the speed they are doing this, the velocity can be berechnet. My English today. It can be calculated via this. But what is important, a 1 micron diameter particle lowers by the velocity of 0.1 millimeters a second. So this is fast, I would say. And a 10 nanometer particle, only the 10th of a micron, so 100 nanometers in a second. So it would take such a particle years, if it's up in the air, to lower it down, to settle down on the surface of our Earth. And here we do not talk about winds and things like that, because in a windy region, of course, the particles are again spilled up in the air and so on. But of course, there exist other processes that remove the particles down or out of the aerosol. We have agglomeration, so the smaller particles are sticking together, building up a bigger particle, and then is lowering with a higher velocity. Or there exists rain out and wash out. Rain out means that the particles act as nuclei. On this nuclei, water droplets are building, and the particle is incorporated into the water droplet, and the water droplet then, of course, falls down on Earth. And when other particles are incorporated in such an existing raindrop, we talk of washout. So, of course, all of the produced and naturally occurring particles which are up in the air will one time come down to our Earth. Here I only want to show you that in our atmosphere, when we here's the diameter of the particles, and this is the distribution, the number. Forget the two other ones. Just look at this upper curve here. The biggest amount is here in about 10 to 20 nanometers. And when we talk about respiratory problems, so our lungs are suffering any disease, only this distribution is responsible here, or is relevant here. And when you think about it, each lungful of air contains millions of nanoparticles. Each. All the day, 24 hours. So on a day, I don't know, billions of nanoparticles are coming into your body. But we do not have to be afraid of it. Here another example, such a tea light candle. When you light the tea light candle at home, for example, this is again the size distribution. So the most of the particles which are evaporated are in the real nano size. Just by using such a tea light candle inside of your rooms, then you produce millions, and so this 250,000 particles in the diameter range of 10 nanometers. And not only such candles and forest, I forgot the word again. What is it? Forest fires. But as well, petrol, diesel, and other things, all are generating nanoparticles. Good. But, as I already told you, we do not have to be afraid of all these nanoparticles which are coming into our body. Our body has routines that they are spilled out of our body. So a 10 nanometer particle will not enter our cells and destroy them. It will end up, for example, in our lungs, and then there is a system which helps us that they are shifted upwards. It takes some 70 days that the particles come out, and then you can spucken, spit them out. Well, I don't know. And how can particles enter our body? Via the skin, via the respiratory system, or by swallowing them. These are the three routines how nanoparticles can come into our body. Well, so of course, again, wide discussions. Since invention of fire, mankind has been exposed to nanoparticles, and today with lots of industrial activity, for example, much carbon black, has been around since early civilizations, and now we have different type of nanoparticles. So what is really different today is that there are many, many different nanomaterials. And I already told this, maybe our body needs many years until it can cope with all these different particles. And some of them, of course, really can be harmful for our body, can be toxic. Good. What is the time? We started at about 7:05. Yeah, I still have some minutes. The nanotechnology toolkit, I think I'll go through this very, very quickly. It's not our main topic here in this evening, but I told you already, I prepared these slides for about 10 lessons. Last year, I think that was about 160 slides. I kicked out some of them. I made some new. And now I ended up with 130 slides. I'll see it. I think you will not have to learn everything of this. I'm not sure how this will work with your exam. But it's just you can look it up. You have my slides then, and maybe the one or the other is interested in such things, and then you have all the information. Good. We have different kind of tools using for imaging and manipulating nanostructures. The SAM, the TEM, STM, AFM, MFM, and deep pen nanolithography. The scanning electron microscope, the first one, SAM, or in German REM. There's one here at the university. We need vacuum. We have a sample which has to be conductive, and we use this so-called Reynolds cylinder. We shoot electrons. We focus them with such electromagnetic lenses, shoot them at the surface of the sample. Then other electrons come out of the surface of the sample, and these can be detected. That's the thing behind it. And we have resolutions of 1 nanometer or even below 1 nanometer. And we can use this to look at the surface of samples. This is just informational, which kind of electrons or even X-rays shoot or come out of the surface by hitting them with electrons. And here, just some pictures which were made by Sam. A zeolite crystal looks like this. Anyone familiar with zeolites? I think they were used. Zeolites were used when Fukushima accident was in 2011. I don't know. Was it 2011? No, they can take up lots of. They can. They can act like a sponge. And the polluted water, which was in the ocean near Fukushima, I think the whole proportion of zeolite which was available on the market was used and thrown into the ocean there to bind as many of the atomic waste as possible, but I think it was not enough. Or other examples here, nanotubes made out of vanadium and so on. Nice pictures, so we can have an imagination how the material looks like. Another electron microscope is the transmission electron microscope. Maybe first of all, the difference to the SAM. We have the specimen here, again in vacuum. We shoot electrons out of the cathode to the anode, and then again condenser lenses, so electromagnetic lensing system. But this time we shoot them through the specimen, and again many lenses and so on. And then we have here at the bottom the plane of the final image. And we have a resolution of already about 0.15 nanometers. So this is a really, really good resolution here. All these aberrations and defects with the lensing systems and so on, I think we do not have to talk about this. This can be compared to the light microscope. The light has a wavelength of about 500 nanometers, and the maximum resolution of optical microscopes is therefore about 1 micron. Because of these aberrations, it's not 500 nanometers, but it's 1 micron. And instead of light with this transmission electron microscope or with other electron microscopes, we have with the wavelength of the electrons, which is really, really small, but the aberrations are a bit higher, so we have this resolution at the end. Just another picture. A gold nanoparticle looks like this. We really see the single atoms. Good. The scanning tunneling microscope. We had this already when we talked about the timeline. It was Mr. Binnig and Mr. Rohrer from IBM inventing it. Tunneling effect, I think you've heard. We have what should I call it? It's a piezoelectric device, okay? And on this piezoelectric device, we have a sharp tip, the so-called tunneling tip. And the best would be if we only have one single atom at the end of this tip. Then we have the highest affordable or achievable resolution of this microscope. Here we have electrodes which are on this piezoelectric device, via these electrodes, it can be steered. Of course, we have to position it at the surface we want to look at very, very accurately. This is done by such a steering system, by this piezoelectric device. And then, again, we need to do it in vacuum, and we need a sample which is conducting. And then we apply a small voltage, and if we are near enough to the surface, the tip is near enough to the surface, then a tunneling current occurs. And this is used, the amount of this tunneling current then is used to show what the surface looks like. The two modes, constant height, constant current mode. Okay, this is details. Here is explained how we can control this piezoelectric device. The X and Y motion, these two directions, is via the 4 outer electrons. If we use the pairs of outer electrons, we can bend it this way or this way. And if we use the outer and the inner ones, the length of this piezoelectric device is changing, and here we can steer or control the Z direction. Here are some nice pictures we can achieve by using the STM. Different metal surfaces. Each time we see the single atoms, so we have an imagination how such the silicium surface, the 111 direction, how this looks like, and other examples. But maybe you can remember this one picture, IBM, written with single atoms. This works like this. We use the STM in the first step, where we make this constant current scan, and we see, okay, here is a particle at the surface. This is the result of the scan, and then we know, okay, this is the exact position of the particle. Then we come nearer with our tip. Then we apply this voltage, and if this applied voltage is high enough that the tunneling current is really increasing, then this atom can be picked and it can be moved, and then we go away with the tip again, and then the particle falls down on the surface again here, or the particle, the atom, I have to say, and here via this we can move single atoms. And at the end we can use the normal scanning mode that we really see, okay, the first time it was here, and now it is really here. We can make an image of the moved atom. This was used from IBM and is really used today in some applications. The atomic force microscope. This is the first microscope I show you, which is not only working under vacuum and with conductive materials. This is working with all kind of materials. What is the main difference? We have a cantilever, so a thing like this, and at the end, again, a sharp tip which is mounted, and then the tip is positioned over the surface, and if we are near the surface, by the atomic forces, it may be attracted, so it's lowering down a bit the cantilever, and when we use a laser and detector system, we can make images again here. 0.1 nanometer is the precision, how we can position our atomic tip. So this is then the resolution of this microscope here. And the distance between the tip and the sample surface is about 50 nanometers. And as I already told you, the tip is attracted or disgusted from the surface, and we are using this system here for making the images. So we see all the valleys and the peaks of the surface. And I already told you this does not only work in vacuum, but also in air and even in liquids. And these microscopes are transportable, so they're only about this size, so they can be taken with. You can take it with you and use it even in the field outside. There's even a company in Austria which is working on these AFM tips. It's the Nanoscience Instruments. Mr. Ernest Fandner, I think, is his name. And this is this SCL sensor tech fabrication. This is from Ernst Fandner. Good. Here's some details again. Of course, again, a piezoelectric control for really exact positioning. It's the same as with the STM, as I showed you here. This piezoelectric device is used here again. And then these forces which are occurring lead to deflection of our cantilever and is measured. We can work with contact mode and we can work with non-contact mode. Well, and here you see pictures of these tips. The magnetic force microscope is very, very relative to the AFM because it's really an AFM with the second measuring system is the magnetic force. So we use magnetic tips instead of non-magnetic tips. And we can make, like with an AFM, if we are not using this magnetization measuring device, we can make just a normal picture of the surface, like with an AFM. So we do this in a first scan. We look at the topography, and then we steer the position of our AFM tip is then in accordance with the topography, and in the second step we only look at the magnetic forces then. And here we see a picture of a data storage disk, and we see these are parts which are magnetized, and here is the gap between the next magnetized area. So this is on the one hand used in hard disks to write with, and on the other hand it can be used in such microscopes, and we really get the information and the knowledge how it looks like. Good. The last tool here I could present you is the dip pen nanolithography. This is very special, but it's used, of course. We use an AFM, but we coat our AFM tip, for example, with alkane thiols or any kind of, let's call it, what is Flüssigkeit? Fluid, thanks. If we use the right ones, they could self-assemble on for example, gold layer. And then they could help us, they could act as a sensor, for example, or things like that. So this is dip pen means we have a pen, we dip into our tinte, what is ink, and we can write with it. And this would mean the same here. We ink or we coat our tip, and then we can use it to write with it on, for example, this small gold film layer. And these alkane thiols then stick to the surface, and the tail which looks out can then act its performance. Good. Newer developments, of course, we can use it one time and then we have to code it again. The tip is not really high technical. We could use such a reservoir in the microchannel, for example, that we could really write greater patterns on a surface, for example. So I already told you we could use such things for the fabrication of biological sensors. I think this is getting now really into detail, and I think such things cannot be asked of you at the exam, but just to get an imagination what is technological state of the art today. These are things which are already on the market. We use in the first step an inking array of this so-called, I don't know what it's, I would have to look it up what MHA is. On this MHA, antibodies can be applied, and different antibodies are sensitive for different viruses or other biological parts we wanna find. Okay, I think we have to make another break here. I'm already a bit, and I see it in your faces that you are as well tired. So let's give us 10 minutes break again.